Hello all, welcome to the part B of lecture 19. In this part we will do hands-on with R. In this hands-on video we are going to do work on another data analysis where let me just first open the R. So what I'm going to do here, we have from the UCI machine learning repository. If we just go there and let me just open my net. Yeah, okay. So this is the UCI machine learning data repository. This is called banknote authentication dataset. So this is from Denmark. It says basically data were extracted from images that were taken from genuine and forged banknote like specimens. For digitization, an industrial camera usually used for print inspection was used. The final images have a 400 by 400 pixel due to object length, distance to the investigated object. Grayscale pictures with resolution of about 600 dpi were gained. Wavelet transformation tool were used to extract the features from the images. And these variants of wavelet transformations, skewness of the wavelet transformations, kurtosis of the wavelet transformations, entropy of images, and the classification, manually done classification 0 or 1, that was done. So now let us start a analysis. So data equal to, we will do read.csv, let me just go quickly to the banknote and all downloads and classification. So this is the dataset name. I have shared this data in the Swarm portal. Okay. So if we just read this, okay, so it does not have any header because looks like this cannot be the name. So it does not have any header. So we have to say header equal to false. Header equal to false. And now we have the data correctly read. All right. Now what we have to do, we have to put the call names data equal to C. First, let us take this name, variance of wavelet. So first one will be var of wavelet. Second will be the skewness, kurtosis and entropy. Okay, skewness of wavelet, maybe I'll just say skew. I don't want to put very large name. Skewness, kurtosis of wavelets, and entropy, and finally last one is the class, which is forged or not. right? So let me just run this. So now you have these names are being given. Okay, so maybe I'll just say wave. Yeah, and now I think this is fine, right? Okay, next I'll just have a look that how many forged cases and how many original note were there. So out of 13,722 1372 observations, 610 of them are forged and 762 of them are not forged. They're true original banknote. So what I'm going to do, I'm going to first plot data dollar variance of wave, comma, data dollar skewness of wavelength, maybe PCH equal to 20. Now what I'm going to do is something I think you will have fun with it. Data dollar, you take the forge or not. See, there is 0 or 1 is there. So what I'm going to do, I'm going to add 1 to it. Okay, I'm going to add 1 to it. Now what happens if I add 1 to it? What is happening, you actually is very simple. I'm just adding either 1 or 0. It was 0 or 1, so all zeros have become 1 and 1s have become 2. Now as a color, color equal to 1 means it will be black, and color equal to 2 means it will be red. Okay, so this is I'm taking making forged or not as the color that I'm going to use. Xlab is let me just take simply variance of wavelength. Okay, and ylab equal to, this is simply skewness of wavelet transformed image. Okay, let me just make this plot. Yeah, let me just zoom it. So this is the data. So now if we see this data is very peculiar. The data has a very peculiar shape. You can see there is a very peculiar shape, and there is bit of a overlap between the two kind of things. So one was forged, which was marked as red, or these are the specimens or points which represents forged note, and the black ones are the one which represent the original note. So we see there is a bit of a overlapping is happening, but mostly they're kind of well separated with a slight overlapping between the two. So can we use wavelet variance and skewness of the wavelet, these two feature, to do the classification? So what we will do, we will set a seed, say sample. First we need to set a seed, so we need a number 1 each to say 1000. So we will take 81. So 81 as setting our seed, set dot seed. Okay, all right, and then n is the n row of data, and m is the ceiling of n times 0.7. So I'm taking 70% for training data set and rest of them as test. IDX equal to sort sample 1 each to n comma m comma replace equal to false. Okay, and then so let me just have this. So this idx is 961 cases have come, and then now df train equal to data idx comma and df test equal to minus idx. So let me just run the whole thing. Yeah, so first thing I'm going to do, I'm going to fit a simple model with wavelet, variance of wavelet and the skewness of wavelet as the feature of simple logistic regression. Fit first model will going to be GLM. Okay, GLM. So what we have is forged or not is as this comma variance of wavelet plus skewness of wavelet, these two, data equal to df train, and then family equal to binomial link equal to logit. All right, now this is what I'm going to do. I'm going to run this model. Now if you run this summary fit 1, so what you have, it's saying that both variance of wavelet and the skewness of the wavelet is going to have a very strong accuracy, strong effect on the both variance of wavelet and the skewness of the wavelet is going to have a on the whether note will be forged or not. Okay, so let us take that. Yes, and then now what we are going to do, we are going to make the prediction on the test data set. Okay, df test dollar probability 1 equal to predict fit 1 new data equal to df test, and then type equal to response. Okay, so now if you see this. All right, so now you can see that these values have come 0 and all this probably a 0.24. So let us see if it is, so mostly they are close to 0, some 0.1, 0.2, and if we just go down to 1, and you will see that they are reasonably close to 0.9, 0.8, 0.9, 0.8. Here is a one point where you got a 0.26, but the probability is less, but actually it is a forged node. So there will be, looks like there could be some misclassification possible. So what we are going to do, we are going to make the prediction. This is the probability of this particular node to be forged node. Now I'm going to make the prediction df test dollar prob 1 equal to df test dollar prob 1. If it is 0 greater than 0.5, we will call it 1, and if it is less than equal to 0.5, we will call it 0. So that means not forged. Okay. All right. Now what we are going to do, so now if I just look into the DF test, so now they're all, so here there are some misclassification we can see, but mostly they're agreeing. So now we are going to, I'm going to calculate a confusion table. Okay, so table predict equal to df test $prob1 comma actual equal to df test $forged or not. Okay, now if I just run the confusion table, so this is my confusion table. Actually predicted 0 and actually 0 was 208 cases and in the test data set. Similarly, predicted 1 and actually it was 1 was 160 cases. There are 24 cases where it was predicted it's not forged but it is actually forged, and there are 19 cases where it was predicted forged but it was not actually forged. So there are possibility of, and let us just check the accuracy. So first I'm going to take the diagonal of the confidence table. These are the correct predictions, all correct prediction. Take the sum of that. These are the all 368 are the total correct prediction, and total number of all test is actually just I can take n row of df test is 411 of them. There are 411 of them. If I just make 100 out of this, so 89.53. so this is my accuracy, 89.53. now if I make I will make a second model fit 2. What I will do is essentially I will just update fit 1 with same model plus few more engineered feature. So I'll just take variance of wave and square them plus skewness of wave lengths and square them, and finally plus variance of wave times skewness of wave. Okay, if I just run this and summary, let me run the summary of fit 2. So looks like variance of wavelets and skewness of wavelet, okay, was, so initially variance of wavelet, okay, if I just run the summary of fit 1, we see that both variance and skewness of the wavelet has effect. But if I run on the forged or not, whereas if I run summary of fit 2 where it shows basically variance of wavelet does have an effect, skewness does not, but the quadratic effect of skewness does have an effect, and the interaction does have an effect. So this is very interesting phenomena, but let's see what is the, whether adding this feature help me increasing the out of the sample accuracy or not. So that will be the real test case. So what I will do, I will just take this guy, copy and paste it here, but here instead of probability 1 I have to take probability 2, and then instead of fit 2 I will just do fit 1, I'll just do fit 2. It will add a new column, it should add a new column, the probability 2. Okay, and then on the probability 2 I will make the prediction. If it is more than 5.5 I will say 1, otherwise I will say it is 0. So now they are making 0, 1. Okay, here is a misclassification. Here was misclassification, it was corrected here. Here is a misclassification. There is misclassification. So we will see, and we can just calculate a confusion table, simply second confusion table with probability 2. And what is the situation of this? Is the second confusion table for this with the second model, and if we just compute the accuracy, simple accuracy, this is 91.97. so 92% accuracy we are getting, whereas from this first model we are getting 89.5%. so nearly 2.5% gain that we are getting. Okay, so this could be accuracy 1, and this could be accuracy 2, and accuracy 2 minus accuracy 1. So 2.4% gain that we are getting because of engineering, proper feature engineering. Now let us see how the geometry of the predictive space has changed because of adding the engineered feature. So I'll do some visualization to understand the effect of feature engineering. Okay, let us try to understand that. So first I'm going to do test data. I'm going to define a test data or dummy variable, and dummy variable data dot frame, and with that I will going to see matrix NA comma n row equal to 1, n col equal to 1, or sorry, n col equal to 2. so test data, and this is the, I'm just creating a simply placeholder. Okay, just a placeholder, and then I'm going to add a call names for test data equal to call names equal to dummy variable equals to this 2. Okay, these are the then variance of wave. All right, so variance, now what I'm going to do, so variance of wavelength is a range of between it is between -7 and 7, and skewness of wavelength is somewhere between maybe -12 to 12. Okay, so I'm going to create this variance of wave, define minus 7 to 7 by 0.1. so basically if I just do that, now you can see that it just creating values between -7 to 7 with a difference of 0.1. okay, it just created these values. Similarly, if I just say skewness of wave is going to take sequence of value between -11 to 11 by 0.1 difference, this is also going to create values between -11 and 11 with a difference of 0.1. okay, equal distance of 0.1. so I'm getting grid. I just created grid. Now I'm going to create a joint grid. Joint grid, how? That's how. So for I in 1 I in variance of wave, for J in skewness of wave, and then dumb variable equal to C of whatever I and J values are there in the thing. And then what I'm going to do, test data equal to R bind data dot frame test data comma dummy variable. All right, so let me just run it. Okay, so it has created test data with 31,162 observations. If I just create that, you will see that it has created a complete grid of 2 values. And now what I'm going to do, I'm going to create a, let me just put a na.omit. So there will be, the first row will be deleted, and now you can see all the values are being created. Now essentially what I'm going to do is I'm going to create, for these all possible values, I'm going to create probability 1 equal to predict fit from the first model new data equal to test data, and type equal to response. Okay, now what I'm going to do is test data, from the test data I'm going to do a prediction, and here is the whole thing. The prediction is basically probability 1. If it is greater than probability 1, greater than 0.5, then the prediction will be pink. Basically it's a forged, that means it's forged. Okay, and if it is less than equal to 5, we will use gray, that means it is not gray color. I'm just going to make this things. Okay, now if you just go there, you see pink and gray. So now what I'm going to do, I'm going to make a plot. I'm going to make a plot that test data dollar variance of wave, test data dollar skewness of wave, and then PCH equal to 20, color equal to test data dollar my prediction color, whatever the prediction color. Now from the above plots, I will just take the labels, X labels and Y labels. Okay. So that is my predicted area. So rate of the one which, so any point that will fall in this area will be called forged node, and any points or any nodes whose variance of wavelet and the skewness of the wavelet falls in this area will be called not forged or original node. Okay. And then what I will do, I can just put the points, essentially df test dollar variance of wave comma df test dollar skewness of wave pch equal to 20 and color equal to df test dollar the forged or not plus 1. So I have to just take this and then, all right, so if I just run this, so now if you see, so these are the points. So let me just, so clearly you can, yeah, I think this is now probably better. Right, now this looks good. So what we are seeing here, that these are the points, you can see there are some misclassification point. These the points which were definitely will be misclassified, and then there are like forged node, but they will be called as a original node, and then there will be nodes which are original but they will be called as forged. So there is a effectively a bit of a difficult, this is sort of a difficult zone. Okay, this is definitely a bit of a difficult zone. All right, now what I'm going to do, I'm going to produce the same plot but for the second model. Remember that second model were developed using the engineered features with quadratic terms. All right, so I am going to copy this thing. So probability 2 with second model, probability 2, probability 2, prediction 2, probability 2, prediction 2, probability 2. Let me just run this. So now if I have the test data, I have now got the second probability and their corresponding predictions as well. So now if I just run this, but the color will be, instead of prediction 1, the prediction 2. Now if I just do that, so now you can see this is a completely different geometry, a quadratic geometry sort of coming up nicely, sort of an ellipse or kind of thing behavior is coming up, which is a very interesting. And now if we just put the points here, right, so put the points here, then we can see that there is it is trying to capture these points, whereas, so let me just little bit increase this guy, so it will be yeah. So this is the quadratic behavior that we are seeing here, and whereas if you just, this is the simple without any feature engineering, we will get a simple linear discriminator, whereas here we are getting a sort of a nice non-parametric quadratic discriminator. Here you can see these points are getting misclassified, right? These points are getting misclassified, whereas here they are not getting misclassified. This point is getting misclassified, but it's better than too many. And similarly, I think if this point is getting misclassified here, whereas, sorry about that, this is better, this point are not getting misclassified. So few points which are nicely not getting misclassified and trying to capture this, and overall out of the sample accuracy is going up. So feature engineering typically helps. Remember that I have not tried the cubic and the other higher order transformations. In addition, we have few more data. For example, we have kurtosis and entropy, which I have not used. So my recommendation is you guys use that and check whether it helps you to improve the accuracy. So I'll stop here, and in the next video I will try to do predictive analysis with a new data set with a new problem. I hope you're enjoying this hands-on real data analysis. Take care. Bye.